in the last lesson, what we saw was, basically different ways to represent a neuron. So one way that we saw to represent a neuron was with our nice little picture, right? Where, essentially we're taking in different features like cell area, cell concavity, and these are represented with different numbers, like, maybe this is like 2 millimeters, and the number of concavities is 3. And we pass that through some sort of formula, what we call our linear function. And if that linear function outputs a positive number, we said we would predict that cell is cancerous. And if not, if it outputs a negative number, we predict that it's not cancerous, right? So the way that we represented this, right, let's say we have, for one single observation or one single cell, we have features of 2 and 3. And we could pass that through, these features, through our function, and we multiply each feature by a corresponding weight, and then have this counterbalance of the bias. Okay? So when we pass these values, 2 and 3, through our function, we get an output of 3, which means that we predict cancerous. And say that now we have a different cell, we want to make this, similar prediction, is it cancerous or not? And here we predict, okay, not cancerous. And, so this was one way. We saw this diagram. We also saw this represented in Python. And then finally, we kind of can see this represented in mathematically, I suppose, with this function z of x, right? Where z of x is our weight, w sub 1, times by x sub 1, our cell area, times by our first weight, times by our first feature, plus w sub 2, our second weight, that corresponds to our second feature. Sorry about that, x sub 2. And then we have that counterbalance, right, of the bias. Now let's just actually write the word bias. Plus bias, where above bias is negative 4. All right. I'll just produce this below. And what we want to do in this lesson, so if you think about it, we kind of have, we always describe the bias as, okay, what's a counterbalance to the rest of the function. And in this lesson, we're going to focus in on the rest of the function. And we'll call the rest of the function right here our weighted sum. Okay, so w1x1, w2x2, everything in our linear function except for the bias, we're going to focus in on this and call this our weighted sum. All right, and you can see what I did was I even just like temporarily assigned it a new variable, a new function, g of x, and just called, okay, this is our z of x. G of x is just everything except for the bias, right? And cool, so that's what we did. So just to bring that home, just to show you that in our, apply that to our example above, if this was our original linear function, 2 times cell area plus 1 times by cell concavities plus the bias, then g of x, again, everything but the bias. Cool. And we can represent it, let's put in the little styles, I guess, like this. All right, now this is where it gets interesting, I think, is that if you just focus in on the weighted sum and you think about kind of, well, I guess we can start by collecting these weights, all right? So what I mean is, this is W1, this is W2, right? This is our first weight, this is our second weight. And we can put these in a vector, 2 and 1. I said vector, but really we know this as a list in Python. But mathematically, we would call this a vector, and we even call this our weight vector. Okay? And then we can do the same thing even with x, with the features of an observation. So previously we had, we said, okay, well, for one of our cells, maybe our first cell, we had cell area is 2 and cell concavities is 3. But we can kind of do the same thing. We can put this in a list as well. We'll say this is 2 and this is 3. All right? So this is our first feature. This is our second feature of a single observation. and we'll call this our feature vector. So this is our weight vector W and our feature vector X. And this is just a rewrite, essentially. And if we want to reproduce this weighted sum of W1, X1, W2, if we want to get from here to here, think about what needs to happen. We need to pair up the entries of the vector by their index. What does that mean? It just means we need to pair up the first with the first, pair up the second with the second, and so on, right? So we need to do pair up 2 with 2 plus 1 times by 3. So we pair up entries by their index, multiply the pairs, 2 and 2, 1 and 3, we multiply the pairs, and then add the products. Okay? And doing that, we get back to our weighted sum, right? So that's it. But the point is that this process can be automated using Pytorch and basically like simplify. Eventually you'll kind of do this automatically in your brain. So let's just see this in Pytorch first. So in Pytorch, we'll import torch, and then we'll do torch.tensor. And tensor is really just like a list. It just knows some extra functions. And this is called W, right? This is our weights. So it's the same thing. Our weight vector W, and then we want our feature vector X. This is our feature vector X. So this is representing cell area, cell concavities, and this is how much we want to weight that first feature and how much we want to weight that second feature. And now take a look at what happens. If we just write W.X, we get back that same value of 7. So Pytorch for us is performing this process of pairing up the entries by their index, multiplying the pairs, and then adding it for us. Okay? And that's kind of the point. We're just going to now re-see this with math. So you can see I kind of did that previously, but let's skip ahead. So this is the same thing that we just saw, right? We just saw that if this is previously what we did, now to represent this mathematically, it's exactly the same thing. It just looks like this. 2 and 1, 3 and 4. And you see this little dot? That represents that we're multiplying one vector times by another vector, okay? And the dot product is that process of pairing them up by their index, right? And then adding. Why did we get two numbers? I think 2 and 3, that's the difference. All right, that's okay. And then 3 and 4 here, right? So I kept the weights the same, but I guess I changed this. And we got an output of 10. And you can see if we want to write this generically, right, then it looks like this. You can see how crazy it is in LaTeX. Okay, and then it looks like, okay, this is called our weight vector. This is called our feature vector. So if we can just write W.X, where this represents this vector, this represents this vector, and then generically these are like the expanding so that you can see the individual entries of our weight vector and the individual entries of our feature vector. And when we take the dot product, again, this is like an expansion or breaking it down to show you what happens. We're pairing up the entries by their index and multiplying the pairs and then adding the products. Okay, and so this is our weighted sum, right? Our weighted sum was this whole thing, and then remember it was everything but the bias. But we can rewrite that as just this, right? And that's kind of nice because it simplifies things, in code. And ideally, it simplifies things in your brain, where you just say, okay, weights are just one vector, and our features are just one vector. And to get the weighted sum, we just dot the weight vector with the feature vector. Okay. Cool. Let's just see, I guess, let's just double check our understanding. That's what I'm doing here. So now I'm just giving you guys kind of a quiz. Here's a new feature vector, 4 and 1. Here's a new weight vector, 5 and 4. And the question is, can you kind of predict what the dot product will be? So if we think about it, it should be, this is my hint, right? So it's 4 times by 5 plus 1 times by 4. So it sounds like 20 plus 4 is 24. That's my guess. X new dot W new, and we got 24. All right, so this was just our weighted sum. To go to our weighted sum to our linear function, right? Remember, this was our original linear function. We can now rewrite our linear function as w dot x plus b, right? And if we expand that, we see that, well, that's the entries of w. Here's the entries of x plus b. And then what our dot product does is pairs up the entries of the vectors by their index and then adds in the bias. And then the point here is, well, like, these vectors can get quite long, so that's why it's really valuable to, instead of writing this whole thing, or this whole thing where we have, here 4 is not actually very long. For a vector of length 4 is not quite as long. We're going to have vectors way longer than that. But they can get very long. But the point is, we can then just always simplify this as w dot x plus b. And so that's what's nice about this thing. All right, and then here's one last thing. You can see, like, I have this, right? So here's w, x, and b, and I write w dot x, right, plus our bias term of negative 20. Another way to write this in Pytorch is the at symbol. Another way to produce a dot product is with the at symbol. Okay? So this gives you exactly the same result. All right? If we just want to use the weighted sum and lop off our bias, there you go. Okay? So that's it. That's the dot product. The dot product is a way for us to rewrite our linear function. So previously, where we wrote, this whole crazy mess, or this whole crazy mess, we're now reducing that down to just this. And the same thing in code. Whereas previously, we would kind of have to write out, oh, def is cancerous of, x1 and w1, or x1, why am I doing that, and x2, where x1 was our cell area, and x2 was our cell concavities, and then we returned, right, w, maybe it was like 2 times by cell area plus 1 times by cell concavities. Well, now we can rewrite this, right? Whereas really this whole formula should be w dot x, right? And the w, we can maybe define that as a tensor. That has 2 and 1, right? We're just collecting our weights like we just saw. And this is x, right? That represents the features of a single observation. So we can here put in whatever, I forget what it was. It was like 3 and 2 or something like that, 3 and 4 later on. So this is kind of a little simpler as well. And this is our whole function now. So if we want to get the same output, we'll just do is cancerous and pass through x. The features of an observation is going to be dotted with this, and let's add, don't forget the bias. So I forget what our bias was originally, maybe it's negative 4, and we get that out. Okay, we got a positive number, we predict cancerous. Okay, we pass through maybe a different observation. We change these numbers, do like 1 and 2. See, it still seems high. So like 0.1 and 1. Oh no. Oh, I guess it doesn't like the fact that I mismatched the type, and we get negative 1. All right. It just didn't, that error was because I had a decimal point. There are ways to correct that, but it's not, let's not worry about it for right now. So that's it, right? This is a rewrite of our linear function where we are rewriting our linear function as the dot product, where the dot product is pairing up the entries, right? Pairing up the entries by their index, multiplying the products, or multiplying the pairs, and then adding up the products. Okay, so we rewrite our linear function as our weight vector dotted with our feature vector plus our bias term. And that's it. Cool. Let's move on to the next lesson.